Zeal Education Society, redefining excellence.
Good morning to everyone. Myself, Dr. Mahadev Unde, Professor in Electrical Engineering Department, Zeal College of Engineering and Research, Pune. In today's video lecture, we are going to learn the three-phase induction motor as an induction generator. Now, when the three-phase induction motor is run above the synchronous speed by some means, that is a prime mover, its armature start delivering power to the load as shown in the figure. See this figure. This is the prime mover, three-phase induction generator. Now, here the delta connected capacitor bank is used to produce the reactive power, and this is a load. Now this generator can be connected either to the load independently or connected to the grid via the transformer. Now such a kind of induction generators are used or manufactured by the Enercon company, which is used for a windmills, whereas the Suzlon uses the synchronous generator for their windmills. This Enercon is a German-made company, and they employ the asynchronous generator. This induction generator is also known as asynchronous generator because it does not rotate at a synchronous speed. It runs above the synchronous speed. Okay. Now, in order to create the magnetic field, its own magnetic field, the induction motor draws the reactive power either from the grid or it may be supplied locally. It may be supplied locally as shown in the figure. Here the reactive power can be generated by three-phase capacitor delta connected bank connected to the induction motor terminals. Okay. Now this reactive power generated by this bank is supplied to the induction motor as well to the load. Whereas the active power generated by this induction generator is fed to the load only, or it is flowing toward the grid only. Now where these induction generators are used? Externally excited generators are widely used for a regenerative braking of a voice driven by the three-phase induction motors. And the self-excited, like this, self-excited generators are used in the windmills. Now, what are the advantages of induction generator? It has a robust construction. We have already learned the induction motor has a robust and very cheap and easier constructions, less maintenance, relatively cheaper. It has a smaller size per kilowatt of power rating or power output. It runs in a parallel without hunting. Needs no synchronization to the supply line is required like a synchronous generator, because it is a asynchronous generator. Now, what are the disadvantages of externally excited generator? The efficiency of externally excited generator is not so good. We cannot use externally excited generator at a lagging power factor, which is major drawback of this type of generator. The amount of reactive power used to run this type of generator requires is quite large. And what are the limitations? It cannot generate reactive volt ampere, reactive power. It requires reactive volt amperes from the supply lines to furnish the or to produce its own excitation. Now see, this curve shows the stator terminal voltage on y-axis and the magnetization current on the x-axis. That is the magnetization curve of the induction generator. It is somewhat similar to the synchronous generator also, or it is similar to the DC generator also. Now try to understand this one. Here it is. Now this is a magnetization curve, upper one, magnetization curve of the induction generator, and this one is load line of the capacitor. Now this is the magnetizing current drawn by the induction motor or induction generator, and on the y-axis there is the voltage generated. Okay. Initially, because of residual magnetism present, the voltage generated in the armature winding of the motor is OA. And because of this OA, if you plot or if you take the projection on this straight line drawn from the origin, so as to cut the magnetization curve at point F, on this line, that is also known as load line capacitor. Now this OA, the EMF generated is OA, and because of this induced EMF in the armature winding, the capacitor current is OB. How to obtain it? From the point A, draw the projection on the straight line and take the projection on the x-axis. So OB represents the capacitor current, and due to this magnetizing current, the EMF generated is BC. EMF generated is BC. This generated EMF BC is increased as compared to OA, and this increased EMF circulates more current, capacitor current, that is the magnetization current, and in this way the EMF get built cumulatively in the armature of the induction generator, so that or up to the what point, up to the where this load line of the capacitor crosses the magnetization curve at point F. So in this way the induction generator develops the voltage. Now what the capacitors are required? See, the capacitor current is on the x-axis and the capacitor voltage is on the y-axis. The current equal to omega CV, that means current is directly proportional to the capacitance value. Now here the C1, see, as capacitor current is higher, the capacitance value is also higher. That's why C1 is greater than C2 is greater than C4. Okay. Now let us have one numerical based on this so that we will get more idea about this. Say 440 volt, 4 pole, 1440 RPM, 30 kilowatt 3-phase induction motor is to be run as a asynchronous generator, that is an induction generator. The rated current drawn by the motor is 35 ampere and full load power factor is 0.85 lagging. Calculate capacitance required per phase if the capacitors are connected in delta. And second is the speed of the prime mover to generate voltage of 50 hertz. Okay. Now have a solution. The power factor is given, cos phi equal to 0.85 and therefore phi equal to 31.79 degree, and therefore sin phi equal to 0.52 into 67. And therefore reactive power required is reactive power which the generator has to draw either from grid or locally supplied by the capacitor bank. Now how much reactive power is required? That is Q equal to root 3 Phi IL sin phi. So root 3 Phi IL sin phi, and that is 14,051 Phi AR, volt ampere reactive. And therefore the per phase volt ampere required is divided by 3, that is 4683.67. Now therefore per phase capacitor current will be, see, as the capacitor bank is connected in delta, the per phase voltage and line voltage is same. The per phase voltage will be 440, and therefore the Phi AR divided by Phi will give you the ampere. Okay, so the per phase capacitor current is equal to this much divided by 440, and that is 10.645 ampere. Once you know the capacitor current, the capacitive reactance per phase will be this voltage divided by current, that is the reactance, and that is 41.35. And XC equal to, we know the XC equal to 1 upon omega C or 1 upon 2 pi FC, and therefore C equal to, if you do the calculations, you will get C equal to 77 microfarad per phase. So this is the capacity required in order to operate this 3-phase induction motor as a induction generator delivering the 30 kilowatt power. Now the speed required to generate the frequency of 50 hertz is, what must be the speed? As we know that the induction motor must run above the synchronous speed. So what must be the synchronous speed? The synchronous speed, or what must be the speed of the asynchronous speed of the induction motor or induction generator, that is n equal to ns plus sns. So ns is 1500 for a 4-pole machine and sns is nothing but 60, that is the slip speed, ns minus n. And therefore it is equal to 1560 rpm is necessary in order to work induction motor as a induction generator, in this case so as to have a generated EMF frequency 50 Hz. Okay, we'll stop here. Thank you very much.